Okay, everyone, welcome to this CSIG-VIS International Lecture Series. And this is the, our 21 phase of the International Lecture Series. Today, we are very pleasure to invite Professor Takayako Ito to give a talk for us. Very welcome. Yeah.
Okay, thank you very much.
Yeah. And at the first day of this the talk, I will introduce Professor Ito. And the Professor Takayako Ito is the first professor of Okumo University, Japan. He received his PhD degree from Waseda University in 1997. He was a researcher of the IBM Research Tokyo Research Lab from the 1992 to 2005. He moved to the Oklahoma University as an assistant professor in 2005, and then he will be a full professor since 2011. His main work on the information visualization, especially graph, hierarchical, and multi-dimensional data visualization. He is the general chair of the HGE Pacific Visualization 2018 and Graph Joint 2022 and many other international conferences. Professor Ito is a very famous professor in the visualization areas. Yeah. So welcome, Professor, to give a talk. The title of the talk is Application and Evaluations of Hierarchical Graph Visualization. It's welcome.
Thank you very much. Thank you for kind introduction.
Yeah.
So my name is Takayuki Ito from Ochanomizu University, Japan. Today I talk about, as introduced, application and evaluation of hierarchical graph visualization. May I share my screen now? Oops. Oh, I cannot now. Yeah,
okay,
yeah.
I need to stop that. Yes.
Yes.
Sir,
Okay.
Sorry. Yeah.
Thank you.
You can share your It's okay.
Okay. It's okay.
It's okay.
It's shared. Yeah. Okay. So let me start my talk on applications and evaluations of hierarchical graph visualization. So this is my career. I was working for IBM Tokyo Research Laboratory since 1992 to 2005. And at that time, I focused on many areas such as computer-aided design, scientific visualization, distributed computing, security, and so on. And I moved to Ochanomizu University as a professor. Firstly associate professor and then professor. And I moved to my research area, mainly info-based and other areas such as multimedia, human-computer interaction, graphics applications, and so on. And I was very eager to visit foreign universities such as Carnegie Mellon, UC Davis, University of Sydney, and the University of British Columbia. So part of my talk includes collaborative work with these kind of foreign universities. Ochanomizu University is public women's university in Tokyo. There are only two universities specifically for the female students in Japan. So this is a main gate and the main hall of the Ochanomizu University. So this is a map of Japan. This is Tokyo, and it's in very central area of the Tokyo metropolitan region, very close to famous places such as Emperor's Palace, Asakusa, Tokyo Disneyland, and also the Haneda airports. So you can easily come to my campus. So if you are interested in, please contact me. So this is a member of my laboratory. All students are female, as I showed. So this is a how to say party of the graduation. So again, all the students are female. So here visualization application focused in my laboratory, including fluid simulation, bioinformatics, business transactions, working fast, human relationships, and live logs and music. So our students focused on very variety of application area in visualization. And today's talk is related to graph. So I talk about my own research topics on the hierarchical graph visualization today. So let me talk firstly about the graph visualization overview, and then introduce three my work on graph visualization and give a general discussion. But I prepared too many slides, so excuse me if I skip some of them. So let me talk about the overview of graph visualization. Graph visualization is computer-powered graph drawing. This is a typical example of computer graph visualization. A lot of nodes and edges are automatically drawn like this. Graph drawing has a long history. So even before the invention of computer. So Euler's diagram is invented in 1736, and Bohr's abstract drawing is invented in 1892. So this history is longer than history of computer. So graph drawing by hand is very hard work. So it's very difficult to draw a large scale graph by hand. So it's easily associated that human want to have a help of computer to draw such kind of large scale graphs. Computers saved graph drawing. So graph drawing by computer has many advantages, such as automatic, quick. So computer can draw in 1 second, and interactive. We can freely operate, freely play with graphs on the display. And publishable. So we can publish this kind of graph drawing results on the web by using web-enabled programming models such as JavaScript or so on. So there are two kinds of very famous visual representation of graphs. The left one is node link diagram, which draws graphs as a set of nodes and links. Right figure shows matrix representation of graphs. So of course, left side, node link diagram is more famous. So in this talk, I focus on node link diagram as graph visualization design. So here are the data types of a graph to be drawn. So it's divided by two types. So undirected and direct, unfixed and fixed. Here, unfixed means that nodes doesn't have their original position. Fixed means nodes have their original positions. In this talk, I focus on undirected, unfixed graphs as the data types of my focus. So application of graph drawing has a very variety, such as social analytics. Here, nodes corresponds to human, and the link corresponds to the relationship, human relationship or friendship. Here, another example of graph drawing in bioinformatics. Here, node corresponds to protein, and edge corresponds to the interaction between the protein. So this kind of visualization is very useful for bringing new knowledge in bioinformatics. So the biggest problem of graph drawing is hairball. It's easily tangled because of too many nodes and edges. So history of graph drawing is a solution for the hairball problem. This is the biggest problem in graph drawing. The most famous approach is so-called force directed, by assuming forces, repulsive forces between nodes and attractive forces between nodes connected by edges. This kind and a repetition of the calculation, force calculation eases the positions of nodes like this, and then calculating over and over, positions of nodes get better configuration like this. So this is force directed node layout has been invented in 1982 or 3 for 40 years ago. So node layout problem has a long history here. Another solution is edge bundling. So by bundling the edges which have same direction like this, we can see simpler structure of graphs like this. Here, this is another example. By bundling many edges which have same directions like this, we can see simpler structure of the graph like this. So node layout and edge bundling is how to say that, two of most famous approaches to make comprehensive graph drawing. What other methods are there to make better graph drawing? Grouping, clustering, hierarchy. This is very important approach to make simpler graph drawing. Here, this is a figure of the bundles of timber. So we often group such kind of many objects to make simpler to understand the amount of things, or simplify the process to deal with this kind of objects. So grouping, clustering, hierarchy is very friendly, or how to say, often used application or approaches for this kind of many items. So this is an example of process to hierarchically understand the idea. This example is so-called the KJ method. So this method is used for the face-and-face discussion. So we write ideas on pieces of papers and paste on the whiteboard, and then group such pieces of papers that describe idea. The left figure shows the basic concept of the KJ method. So we make many ideas and write into pieces of papers, and then make a group of papers to arrange our ideas. And then we can connect the groups by drawing edges. And then we can clarify the relationships of ideas. So this is a very typical method to hierarchically understand the idea. So hierarchical graph visualization is very close to this kind of drawing. So this is very practical and reasonable methods for understand the relationship structures and how to say that, simplified structures. So hierarchical graph visualization is very reasonable as shown in this picture. So this is an example of node clustering for visualization. So we can see simpler structure of the graphs by clustering nodes into several groups. So this is a basic idea of the hierarchical graph visualization. So hierarchical graph is very effective for the edge bundling. Here, and this is before edge bundling, this is after edge bundling. So by applying edge bundling for hierarchical graph, we can see very high level and low level structure of the connection simultaneously by applying this kind of hierarchical edge bundling. So similarly, this is before edge bundling, this is after edge bundling. So similarly, we can see high level and low level connection relationship of the graphs by looking at this kind of hierarchical edge bundling. So hierarchical graph is also effective for edge by using with edge bundling. So let me summarize the overview of the graph visualization. So graph visualization is computer-powered graph drawing. So there are data types according to the direction, node positions, and also the time varying or multivariate. And also graph drawing has a lot of applications, including social analysis, bioinformatics, traffic, communication, blah, blah, blah. So graph visualization is a very attractive research area because we have a lot of applications. And there are techniques for the graph visualization, including node layout, edge bundling, clustering, hierarchy. So our talk, this talk focus on clustering hierarchy for the graph visualization. Today's talk introduces the speaker's 3 studies on hierarchical graph visualization. But constraint of time, so let me, excuse me if I skip some of the slides. I prepared too much. So excuse me that I may skip some of them. So today, I introduce 3 my work on hierarchical graph visualization. The first one is multiple category graph visualization. So this is a jointly with Chris Mulder and Kwan Liu-ma in UC Davis, and also the Jun Sese in Ochanomizu University, and presented at IEEE Pacific Visualization in 2009. So I visited UC Davis for 2 months, just 2 months, and this had a discussion with Kwan Liu, and also I had a data of the bioinformatics made by the Jun Sese. And I talked about visualization of this data in bioinformatics with Kwan Liu, and invented new methods. I implemented in 3 weeks or something, a very short time at UC, during the visit to UC Davis, and write a paper for the Pacific visualization. This is very short story, but very successful story. So let me define multiple category graph. This is a graph consisting of nodes belonging to 1 or more categories. So here, let me introduce the drawing example. Here, color corresponds to the category. So there are 3 categories drawn by orange, green, and blue. So, and also the node may have more than 1 category. Here, this node has 2 categories. This node has 2 categories. This node has 2 categories. So category belonging information is described as array for each node like this. So easy example, let me show the easy example of social networking to visualize by my method. So here, node corresponding to person, link corresponding to friendships, and category friendships are community or keyword of each person. Here, some people like cake, some people play violin, some people like soccer. So let me show all 3 categories like this. So which part of this graph are you focusing on? So maybe some people may focus on tight subnetwork like this. Here, this is a complete subnetwork here. And also here, multi-community person. This is a multi-talented person who are interested in cake, who plays a violin, and who like a soccer. So multi-talented person here. And also he is a hub person connected to many soccer players like this. So there are many types of partial interesting portion of graph like this. So we'd like to clearly visualize this kind of interesting part of graphs. So this is a basic idea of this study. Requirements for visualization includes place common category nodes closer, reduce the sum of lengths of edges and the number of intersections among edges, avoid the cluttering of nodes, maximize the screen space utilization, reduce the computation time. Here, just first one is multiple category graph specific requirements, and the others are the general requirements for the graph visualization. To satisfy this kind of requirements, we proposed hybrid layout algorithm in combining force-directed algorithm and the space-filling algorithm. So this is a proposal, hybrid space filling and force-directed graph visualization methods. So this is the approach. Firstly, we apply the hierarchical clustering to nodes. And then we have layout. And then we provide interaction mechanisms. So this is the first step. So we divide categorized nodes and non-categorized nodes in a top hierarchy. And then we apply clustering to categorized nodes. So this is colored nodes. And also we apply the clustering for the non-categorized nodes here drawn in gray. And then in a leaf, as a leaf nodes, we see a categorized nodes here and non-categorized here. So this is a data structure and a layout. So here, this is a categorized nodes. We draw categorized nodes here and enclosed by rectangle. Rectangle corresponds to the branch node of this data structure. Similarly, we draw the non-categorized nodes here and enclosed by the rectangles. Here, rectangle corresponds to the branch node of the tree structure, like here. And then we draw the rectangle corresponding to the top of categorized nodes. Here, this branch node corresponds to this brown rectangle. And finally, we draw root nodes as the biggest rectangle here. This is a space filling layout we implemented for this visualization. So rectangle parking technique, originally I proposed rectangle parking technique for tree visualization in 2004 and 2006. And this visualization is similar to tree map, but better than tree map on aspect ratio of rectangular regions and a flexible cluster positioning by referring templates. So this templates describes the position, ideal position of each node. By referring this one, we calculate this kind of positions of nodes like this. So we apply two types of layout algorithms. Here, for the non-categorized nodes, we simply apply the rectangle parking. And then we apply new approach, hybrid rectangle parking and force-directed approach, new node layout algorithm for specific for this layout, this method. So this is a processing flow of hybrid layout for categorized nodes. Firstly, we made a cluster of categorized nodes like this. And then we generate high-level nodes. So here, node corresponds to the rectangle here. A cluster, this node corresponds to the cluster of this cluster. So this node corresponds to this cluster. This node corresponds to this cluster, like this. And then we generate 6 edges by bounding these kind of real edges. And here, weight is proportional to the number of links. And also, the connect clusters of edges here if their category is common, even if there is no links. For example, this cluster and this cluster is not connected. But in this high-level graph, we connect this because these have same color. Similarly, this cluster and this cluster doesn't have any connection, but we connect these two clusters in the high-level class because they have same color here. And then we apply the force-directed layout for the cluster graph, high-level graph here. And then we describe positions of result of force-directed layout as a template here. By referring this template, we calculate final positions of these rectangles by rectangle parking. This is a hybrid layout algorithm for the categorized nodes. So, and also we draw nodes like this. Categorized nodes are drawn as colored circles. and the colors of nodes denotes categories, and radii of nodes denote number of links, and 3 colors denote that the nodes belongs to the 3 categories. And here, brown and gray dots, there are non-categorized nodes. This is our non-categorized drawing nodes. And also, there are 3 levels of thickness and transparency of leaks. I'd like to talk about it later. So this is a comparison between the proposed technique and conventional, existing space filling techniques. Here we took 1.3 seconds, 1.2 seconds, 4.7 seconds. So if we don't apply the space filling, but just to simply apply the force directed technique, it takes more than 200 seconds. So our proposed technique is first, and also the better visualization. So this is a comparison, a numerical comparison of these three visualization by 3 criteria. Node distance between similarly colored nodes, and edge length, and the number of intersection. All 3 criteria, smaller is better in all 3 criteria. Here, the left visualization result had worse results in edge length and number of intersection. And the second visualization had worse in this one, node distance. And this proposed technique shown in pink here had better results in all 3 criteria. So proposed technique is evaluated, numerically evaluated better than conventional existing implementation. So let me skip this page. We can implement focus plus context interface like this. So we applied this visualization to active biological data, including more than 6,000 genes as nodes, more than 7,000 gene-gene interactions as edges, and 10 conditions of gene expressions as categories corresponds to the colors of nodes. And the goal of this visualization is discovery of half or multifunctional genes, and also the subnetwork discovery by the conditions. So this is a visualization example, same as shown in a comparison. Here we can see the hub gene discovery connected to many other genes. This is a very important gene because hub gene have interactions with many other genes. So here there are multifunctional genes. There are very this is very important for the lives of the because they have many functions. And this is very important, well-divided subnetwork. Here, dark orange and dark green is two conditions of gene expression. And these 2 expression is very related to this subgraph. So this isolated subgraph is related to brought by the 2 gene expression. In other words, this gene-gene interaction is very related to 2 conditions of gene expression drawn in dark orange and dark green. So this kind of discovery is very important in bioinformatics to have to verify the experiments of gene-gene interaction or gene expression. And also we have separation of common condition gene clusters. So here, D and D prime, E and E prime, F prime, F prime, they have same color corresponding to same condition of gene expression, but they are separated. So these 2 groups didn't have interactions. So this is very mysterious for experiments of bioinformatics. So even experts of bioinformatics didn't understand why they are separated. But in other words, we may have new knowledge because of new knowledge from the separation of this kind of similar genes into two groups, D and D prime, or E and E prime, or F and F prime. So this is a kind of mysterious, but maybe a new discovery. So this is also very important because it's very difficult to find without visualization. This is the power of graph visualization to find this kind of new things. So actually the bioinformatics expert was excited by this visualization results. So let me go to the second topic, keynote separated graph visualization. So this is jointly with Carsten Klein. So I visited University of Sydney in 2014, 8 years ago. At that time, he was a researcher in the University of Sydney, and now he's working for the Constance University in Germany. So, and then we developed new algorithm for the graph clustering and layout. So specifically for the human relationship graph, and published on IEEE Computer Graphics and Applications in 2015. So next year of my visit to University of Sydney. So here, let me define a human relationship graph. So human relationship graph, node corresponds to human, and edge corresponds to the relationship. So typical example of the paper-course-ship graph or friendship graph on social networking services. So here, and this is a professor. This is a picture of myself 10 years ago. I was much younger, of course. So there are groups of students here. And there are other group of students here. There are another group of students here. Maybe they had works on information visualization. They had works on the computer graphics. They had works on multimedia. So maybe they are divided according to the topic of researches. These are illustrations of my students of my laboratory. So here, characteristics of this kind of graph is that, so graph includes authority persons, and also the other persons are categorized clusters according to topics of them, like this. This is a typical relationship of paper-course-ship graph. So let me show you another example of friendships graph on social networking service. So there are two famous violin players and their fans. And they are, how to say that? They are connected to both of these violin players. So these are common fans of these two players. So they are very famous soccer players, and they are fans. So commonly, they are connected to these two players. So they are common fans of these two famous players. So similarly, characteristics of these graphs include that there are authority persons, and the other persons are clustered, grouped according to their topics. For example, violin player or the soccer player. So these kind of topics divide other persons. So this is a very typical characteristics of human relationship graph. So issues of node clustering for this kind of graphs. So community finding schemes are well applied for this kind of graphs, but these extract subgraphs which have dense edges, but key nodes corresponding to famous persons in kind of human relationship graph are involved in large clusters. But often we want to separate such nodes from the clusters. For example, this is a famous person, so connected to many people, but by applying ordinary clustering algorithm based on density of connections, this kind of important nodes are hidden in a large cluster like cluster one. So if apply the high-level drawing of the clustered graphs, so in this case, this node is hidden in a cluster like this. So it makes difficult to find this kind of important nodes in a graph drawing results. So key nodes and many edges are hidden inside clusters in this case. So we don't think this kind of visualization result is good. So we'd like to improve by separating this kind of important nodes from clusters. So if we can separate this kind of important nodes from the clusters like this, we can see the relationship between such kind of important persons and also other clusters of other people like this. So this is a basic idea of the graph drawing proposed by our group. So we applied a key node aware metrics, two metrics for node and node to node distances, including this commonality of connected nodes and also this similarity of feature vectors corresponds to the topic of the person. So these two metrics is used for the node clustering and node layout in this technique. So there are data structures and node distance. So there are data structure very similar to ordinary graph drawing. And this is a node distance, just a linear combination of two metrics, including similarity of topics and also the connection to same persons. So this simple equation corresponds to the two metrics explained in the previous here. So we applied hierarchical clustering, applying the two metrics, and then we applied clustering, cluster layout, and then node layout. So like this. So we also applied edge bundling. Let me skip the detail of edge bundling implementation in our technique. So let me show you the example data set. This is a paper authorship data. So including more than 500 papers by NBAF, and also the more than 1,000 nodes corresponding to authors and 11,000 edges corresponds to the authorship. So, and also we calculated feature vectors from the paper titles. So this is a frequency of predefined 12 words for each author. So, and we constructed 12-dimensional vector for each node corresponds to the authors. So this is a predefined 11 and 12 words will appeared in the paper titles of the this data set. So computation time was 2.5 seconds for clustering and 8.8 seconds for node layout. So this is a example visualization. This is a clusters correspond to the circles. Here, by zooming up, we can see many nodes in the circles like here. And also the color according to the feature vectors of each person. So corresponds to the topic of their major papers. So, and also we can control the number of edges to be displayed here. So here, number of edges, displayed edges are reduced to comprehensibility. And also here, edges only connected to the specified node is displayed here to clarify the relationship, authorship of particular person. So here, this is an example of 170 clusters by our algorithm. Here, color denotes the nodes of the degree of a node. So bright red nodes correspond to important nodes. So, and a black node correspond to non-important nodes. So here, let me zoom up to these three clusters. And here, there are two very bright red nodes corresponding to very key, very important person, which has many co-authors, maybe for professor or other famous researcher. So two key nodes are separated from large clusters. Here, there are bright red nodes corresponding to important persons. Important persons are separated from large clusters in our methods. This is a preferable clustering results in our study. So here, another results, 159 clusters by common clustering algorithm. Here, important nodes are hidden in a large cluster. Here, we don't prefer such kind of clustering results because it's difficult to find this kind of important nodes from the clustering results. So our technique is better in this study. So let me show you the case study with course-ship graph. Here, 12 colors denote the topics or most important topics of each author, each person in this graph. Here, I skipped to draw edges to clarify the distribution of topics like this. Here, these are clusters of paper authors corresponding related to the genetic. Here, clusters of authors related to the topic molecular. So this is a cluster of authors related to the topic expression. So this is another visualization by coloring nodes by the degree of nodes. Here, bright nodes correspond to important person. Important persons are in smaller clusters like here, here, here. So we could separate this kind of important person from the large clusters and to clarify the relationship between the important persons and other persons. So this is very successful results in our study. So let me zoom up to two clusters. Here, there are 4 very important persons, 2 persons here, 1 person here, 1 person here. So let me introduce the relationship between these 4 important persons and the other persons. So here, let me call this cluster A. And so including 2 important persons. So this is a connection of 1 person in one of the key persons in cluster A. So there are many connections with particular fields of people, such as people in molecular and polymorphic braiding, genetic expression. So he or she has connection with people which are related to particular fields of people. So in the same cluster, there is another key person in cluster A, the same person. So let me compare the connection between 2 key persons. And this is the first person. This is the second person. Let me show you again. This is the first person. This is the second person. Second person has more variety of connection with many fields of people. So both they are very important persons in this data set, but connection is a little different. So the first person has a connection with authors related to specific particular topics. Another person has a little similar connection, but more variety of connection with many fields of people. So this kind of difference is also easy to observe by applying clustering of our technique. So let me focus on other clusters. Here, cluster B and C. This is a connection of the key persons in cluster B. So many connection with other fields of people. So here. So many other people. And cluster C, also many connection of uncolored fields of people. So here. Most of connection with this person is with a person's uncolored corresponding to uncolored person. So this suggests that we colored 12 by selecting 12 important keywords. But this visualization suggests that the 12 colors is not sufficient. So maybe we need more colors to understand more colors to understand the relationship of this kind of important people with other people. So it's very difficult problem. 12 color, I think 12 color is enough. If we have more colors, if it's difficult to distinguish between the similar colors, so which number of color is the best? This is a very difficult problem. So, but if we understand, if we want to understand the relationship of this kind of important people, we may need more colors to understand the particular fields of their connection, like here, 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 like this. So it's very difficult. But anyway, so this kind of clustering and layout makes easier to understand the connections, important people and other people. This is a target of our study, and we achieved very successful clustering and layout algorithm here. So this is a numerical comparison. So this is a number of nodes of clusters of 2 key nodes. Here, smaller numbers shows that important nodes are involved in smaller clusters. So this is a preferable result in our study. And this is a number of edges inside clusters. Here, smaller number of edges are hidden inside clusters. This is also the preferable results in our methods, in our study. So numerically, we achieved better results comparing with the common clustering algorithm. And also, this is a subjective evaluation with 13 university students in measuring in computer science. Here, our technique got, if the first data sets are already shown in this talk, so many of the students preferred our technique. And also, in another data, many of the students preferred our technique. So subjectively, our technique was also successful. So let me move to the last topic, evaluation based on sprawl and clutter. And this topic is presented at IEEE Transactions on Visualization and Computer Graphics in 2020, and also presented at IEEE Pacific Visualization 2020 and got an honorary mention. So this is jointly with Jipen Liu, Jessica Dawson, and Tamara Mzna. I visited University of British Columbia, Tamara's lab only for 3 weeks and started this topic. And after coming back to Japan, I continued this work remotely with these authors. And finally, we could publish this work and transactions of visualization and computer graphics. So this is an easy question. Which is easier to understand? These two graph drawing has the same connection. I expect everyone select the right one. I expect no one select the left one. And this is, I think, trivial. But how can we explain why the right one is better? This is not an easy question. So there are metrics to numerically evaluate the readability of graph layouts. For example, proper distance between two nodes, no overlap between a node and the edge, and less cluttering by crossing of edges. They are very famous criteria for the readability of graph layouts. So by satisfying this kind of conditions, we could achieve comprehensive graph layouts, such as a right example here. This is much better. Please see this figure and 3 conditions. You can see that proper distances between two nodes, no overlap between a node and edge, and less cluttering by crossing of edges. So I think this drawing satisfies all 3 conditions. So by applying this kind of metrics, we can achieve better graph drawing, graph layout. So how about hierarchical graphs? Here, let me say node corresponds to the smallest dot. Edge corresponds to the connection, and the meta node is clusters of nodes. And again, in other words, circle surrounding a group of nodes like this: node, edge, and meta node. So I showed the results of the hierarchical graph visualization like this in the previous topic. In this case, we can see the group of nodes here and a group of nodes here, group of nodes here. We can draw a circle surrounding these groups. This is meta node. So let me show you the meta. Let me call this kind of the surrounding area meta node in this topic. How to explain the quality of layout of hierarchical graphs? This is a difficult question. We surveyed this issue, but there are very small number of previous papers focusing on the quality of hierarchical graphs. So readability problem includes that. So let me skip this one. So sorry. So we extend these three conditions to hierarchical graphs. So to evaluate the quality of hierarchical graph visualization results. So these three conditions correspond to node versus node condition, node versus edge condition, edge versus edge condition. We extend of these conditions to hierarchical graph as meta node versus meta node versus edge, edge versus edge. And this is an illustration of three conditions of hierarchical graphs. So relationship between two meta nodes, relationship between meta nodes and edge, relation between edge and edge. So we define three metrics for these three conditions. So this is the main main issue of this topic. So penalty for hierarchical graphs. So we define two kinds of penalty for the visualization of hierarchical graph. First one is sprawl, corresponds to velocity of space due to the sparseness. Here, left side has a dense area. The right side is sparse. So here, right side has larger penalty. So left one is the better result. And a clutter corresponds to collisions among meta nodes and or edges. So there are three types of cluttering of meta nodes or edges. First one is overlapped area of two meta nodes. Second one is overlapped legs of meta node and edge. Third one is cosine between two edges. We apply three metrics here, these three metrics to evaluate the quality of graph visualization results. So we call these two metrics as sprawl plus clutter. Hi, here. This is the result of calculation results for the penalty of hierarchical graphs. Here, first one, there are some overlaps here. So here we calculate sprawl metrics as 11.32. So here we have more cluttering here, more overlap here. So penalty value is larger, 14.25. Here, and there are little overlap, but sparse. So in our metrics, so penalty is 21.57, so larger. So how to calculate this penalty? So let me talk how to calculate this penalty. So penalty for hierarchical graph. This is a formulation of the penalty applied in this technique. The calculate of penalty for meta node versus meta node versus edge, and also the edge versus edge. So here penalty is a sprawl value multiplied by the maximum of clutter and make a square root here. So this is a calculation of penalty. So here sprawl is calculated as area of display space divided by the sum of node area. Clutter is calculated by the sum of penalties like this. Here, a penalty function f is defined. This is calculated from the function of area, length, cosine x. Area, length, and cosine corresponds to the three penalties here. 1, 2, 3. This is the area. This is the length. This is the cosine. This is the input of the function f here. So how to define the function f, I'd like to explain in the next slide. So function for clutter. So this is defined as monotonically increasing function with either of following. Either of overlapping area of two metanodes, overlapped lengths of metanode and edges, and a cosine between two edges. So this is a definition of the function f. So we defined according to these requirements, rules. Rule 1 is exponential function customized by psychological experiments. This is inspired by Stevens power law, very famous psychological experiment. So rule 2 is positive minimum value. So rule 3 is constant maximum value. Rule 4 is 1.0 at the median input. So these are formulation of the function f. So detail of the function f is defined in a paper. So if you are interested in, please see the detail in the paper. So this is an example 1. So node to node versus node overlap. Here, this is a 4.3. This is 14.4. This is 21.1. So here, a penalty for metanodes gets larger if the area of overlap gets larger. Example 2, node to edge overlap. Here, almost no metanode overlap with edges. Here, penalty is 5.4. Here, there are some overlap between edges and metanode. They penalty gets 39.8. Here, nearly max. The overlap gets nearly max. Here, sorry. There penalty gets larger, 97.5. Example 3 is low or high sprawl. Here, these are same graph. Here, there are some clutter overlap of metanode and edges or two metanodes, but low sprawl, it is dense. So the right figure has no clutter, but these are sparse. So here, a penalty for clutter is much larger in the left side, but sprawl, penalty sprawl is much larger in the right side. So in our definition, by calculating using these two metrics, we have that sprawl is better in the left side. So in this matrix, in our matrix, left figure is better. So this is a real world graph. So here there are same graph, layouts of same graph. So here in this case, we say that this right side is better. So because sprawl is much smaller here. So this is another real world graph here. This is orthogonal angles and this is glancing angles. In our matrix, left side is much better. So the detail of these results are described in the paper. So if you are interested in, please check it. So finally, I'd like to talk about the limitation of future vision of this work. So the first limitation is that we don't have objective verification of appropriateness of this evaluation metrics. So we need to verify how this metrics is appropriate. Second limitation is that we consider only sprawl and clutter. So we don't incorporate no other metrics. So we need to discuss if it's better to incorporate other metrics in our study. So the first future vision is that pixel-based implementation is also practical, not only the geometry-based implementation. So pixel-based implementation is sometimes very important for how to say real-world usage of the graph visualization. So second vision is evaluation of meta edge. Sorry, evaluation of meta edge corresponding to Bartle's edge. So we don't apply the edge bounding in this technique, but if we apply the edge bounding, so this is a groups of edge correspond to meta edge. So we need to another evaluation for the meta edge if we apply M's boundary. So third vision is evaluation of evaluation. So we want a user experiments to verify the appropriateness of this technique. This is very related to the first limitation. So we haven't verified the appropriateness. Last one is layout optimization uploading explorer. So my student is working on this area, this issue. So how to optimize the layout, how to satisfy better layout, satisfying better explorer metrics. So this is very important to how to say that practical usage of these metrics. So finally, I'd like to give a general discussion of hierarchical graph visualization. So hierarchical graph visualization has important roles for the scalability of graph visualization, interactivity of graph visualization, and also the representation of real worlds in the graph visualization. So hierarchical graph visualization has very important in a visualization of large scale or visualization of real world data. And also we'd like to explore application development of hierarchical graph visualization to discovery of approaches for the new algorithm. So how to say, new application brings new algorithm. So this is my policy. So I'd like to find opportunity for the development of new application. Then also a more numeric evaluation is important for the approaches of automation of visualization optimization. So I'd like to apply the optimized layout, applying this kind of layout metrics. And also, therefore, our next step includes layout optimization. And also, I'd like to discuss aesthetic-based numeric evaluation, not only the mechanical or something numeric, how to say, objective evaluation, but also the aesthetics-based. So it's very difficult question, but I think recent machine learning technique can be applied for this kind of evaluation. This is the final chart. I'd like to advertise Graph Drawing 2022. This is the most traditional. This have 30 years of history graph drawing conference. So this year we have a graph drawing symposium in 20 to 16th in September in Tokyo. This is first time in Asia, first time in Japan, first time in Tokyo. So paper deadline has gone, but poster deadline is still alive. So this is August 10. We have almost 1 month. So you can write 2-page abstract and submit to Graph Drawing 2022. See you at Tokyo soon. Thank you very much. Hello?
Okay.
Hello?
Okay. Thank you very much.
Yes.
Yeah, it is a very good talk. Is there any questions?
Is there a way to explore how to balance between clutter and sprawl penalties and evaluate the effects of different penalty functions? Oh, good question. Yeah. It's very difficult question because we don't evaluate the effects of different penalty functions. Yeah. That's one reason why I need user experiments, user evaluation, because balance between clutter and sprawl is very subjective and based on some preference of users. So I think user experiments, user evaluation is needed to balance between two metrics. And also evaluate the effects of different penalty functions. How to say? At least I need to explore the balance of 3 metrics penalty, such as meta node to versus, meta node to edge, and edge and edge. Anyway, user evaluation is very important step to balance these kind of penalty functions. Yeah, I think this is the most important answer.
Okay. Any other questions? Yeah. Thank you. Any other questions? Professor Ito, I have a question.
Yeah.
Yeah, I think you do the visualization for including the human is very important. And I have a question for the layout of the graph. If the graph, the load of the graph is very, yeah, it is large and large. So how to do the layout for the graph with many nodes?
Yeah, very good question. Because our data set is just thousands of maybe 5,000 or something. But yeah, in this case, if we have maybe 1 million of nodes, we need to apply a hierarchy clustering twice. So maybe the parent nodes and then grandparent nodes or something like that. So, but we haven't had such implementation. I don't know how this is difficult or how this has a problem, but yeah, I think multi-level implementation is needed for larger graph, including millions of nodes. Yeah.
Yeah.
And, yes. Yeah. Another question. Do you think we can apply the metric to dynamic? Yeah, dynamic graph. We haven't thought about a dynamic graph, but maybe important to simply add the metrics about the stability along the time axis. So long years ago, when I was focusing on the hierarchical data, not hierarchical graph, just hierarchy. So we applied stable layout for the hierarchical data along the time. So in this case, we just added the metrics of stability along the time. So this is a simple idea to extend our technique. And other metrics applicable to edge bounding as well. Yeah. For the edge bounding, so we need to change the edge versus edge metrics because we apply the edge versus edge metrics as a cosine of two edges. So because this is a this is based on past evaluation, user experiment results that smaller cosine makes confusing visualization results. But we don't need to think of cosine if we think edge bounding. Instead, we need to emphasize the meta node to meta edge penalty. We need to consider not only length but thickness of bundles. So this is what we need to think about edge bounding with penalty. Yeah.
Okay. There are some other questions in the WeChat echo. How do you think we can identify the subgraph with some visualization?
Currently, I don't have any ideas because always I identify subgraph first and then apply to visualization. Visualization first and then identify subgraph. It's a difficult question. I don't have good idea, but I think if you want to find subgraphs from visualization, I don't think node link diagram is good. matrix representation is better. So it's different work it should be different work. How do you think we can identify the subgraph? Same. Is there some recommended interaction on visualization approach? Is this same question? I don't understand it. Is there some recommended interaction or visualization approach? Yeah. As I said, if you want to find subgraph from the visualization results, matrix representation is better than node link diagram. Yeah.
Yeah. There are also a lot of questions. Do you think we can apply the metrics to the dynamic graph as well?
So sorry, metrics for the dynamics graph?
Yeah.
Yeah.
Metrics to the dynamic graph. Yeah.
Yes. I think metrics for dynamic graph is that I want to simply add a stability. So for example, movement of nodes. This is a important metrics for the dynamics graph. Yeah. Graph layouts are often guided by objective energy loss functions. Is there any way to incorporate user interaction in the layout process? Oh, yeah. I might see the paper to partially user intention in the layout process. User intention. One idea is describe ideal positions of nodes first, and then refer the ideal position while the energy function. Energy minimization process. This is very closer to idea of my previous study on hierarchical data visualization. Yeah. By describing ideal positions of graphs, we can see we can how to say that we can make the layout result closer to the ideal position of users. Yeah.
Okay, thank you. There are also a lot of questions in the WeChat window. Graph layout are often guided by objective.
Sorry. I answered now.
Yeah. You can.
Sorry. What is user's perception on the movement of diagram?
Yeah.
Yeah. What is user's perception? Oh, sorry. Excuse me. I haven't focused on perception or evaluation of dynamic graphs, so I don't know very well. But especially, I want to see the change of movement of nodes, or change of intersection of edges. This kind of dynamic change may destroy the mental map of users. So we need to consider the change of positions, change of intersection, change of overlap. Yeah, this is an important metrics. Yeah.
Okay. Yeah, many students have been listening for your talk. So many questions.
Thank you. Yeah, it's a great pleasure for me.
Yeah. Are there any other questions? Yeah, other questions? Okay. Maybe no questions. Yeah. Thanks again for your very interesting talk. Yeah.
Thank you very much. Thank you very much. Yeah, it's very enjoyable. Yeah, thank you very much.
Yeah. Maybe welcome you to Chandler again.
Yeah. Really.
Yeah, I remember. Yeah, I remember you go to Shanghai in 2000.
Yeah.
You know. Yeah.
I enjoyed so much. Yeah. Again in the near future. Yeah.
Okay, that's all. Thank you very much.
Thank you very much.
Yeah,
yes.
Thank you all for the attention. Yeah.